The next equation we want to talk about is called the CMC color difference equation. The basis of the development of the CMC equation was an extensive study on visual acceptability of color differences in all regions of color space. It was based on visual observations. So the CMC is defined by a set of color difference equations developed by the Color Measurement Committee, CMC, that's where that comes from, of the Society of Colorists in the United Kingdom. And this is one case I didn't spell it wrong. That's how they spell things over in Britain, right? Got a U in color. So these were developed in the United Kingdom actually by textile chemists, textile industry. Here is the equation for delta CMC. You can see now we're getting a lot more complicated than just our regular delta E. You end up with a delta E, but the delta E CMC is a little bit more complicated. And basically, if you want to look at it, if you look at this equation, in a way, it's a little more complicated, but it's very similar to our regular delta E, right? If we take away these bottom factors here, delta E equals delta L squared, delta C squared, and delta H squared. The difference is these numbers on the bottom, you could think of those as, for lack of a better term, as fudge factors that make the equation correlate better with how we actually see the numbers instead of what we saw in the C-Lab type area. We're not really using a different color space. We're just using the same LAB color space and using different numbers to describe the L, C, and the H. These are adjustment factors, I guess you might say, in terms of the equation. A couple of things here. Constant L and C are defined by the user and the weight, the importance of lightness and chroma relative to hue. We can actually weight each of those values a little bit different based on what our actual data shows. So that gives the equation much more flexibility to account for differences in different parts of color space. And that's where the value comes from. So again, looking at the main equation, we can see that it's very similar to delta E, except that the weighting factors were added to make it correlate better with visual observation. The CMC equations utilize C-Lab, L star, C star, and H star values of a color standard to determine the semi-axis lengths of an ellipsoid containing all colors which be visually acceptable when compared to the standard. Acceptability ellipsoids' three semi-axes are defined in the L, C, and H directions. This is what our volume looks like. And we have our equation down here at the bottom. We have a L axis, a C axis in one direction, and an S axis in the other direction. I said it's kind of like I mentioned Australian rules football, kind of a blimp-like shape, if you want to think of it that way. In this case, the L is the longest axis, and in this direction we have C and H. So these two don't necessarily have to be the same size, or really aren't the same size. So if you were to look at this cross-section that kind of looks like a circle here, it wouldn't necessarily be a circle, but it would probably be more like an oval. And you can adjust those lengths based on how we put these L and C values in there, based on visual calculations. Here's another picture of that, and kind of shows it in terms of how it falls on our LAB plot. Chroma in this direction, hue in this direction, and lightness would be in this direction, coming out of the slide in terms of what we're looking at there. Another picture of it, standard would be in the center, and we have our L direction, our H directions, and our C direction. And again, what this is showing is we would have a standard that's right in the center there where it's pointing, and then in our color space, any color or any point, any sample that fell within this volume would be considered an acceptable match. Anything that fell outside of it would be considered unacceptable and would fail. Again, the closer you get to the center, the closer it is to the color. But depending on which direction it's off, allowed to be more or less off depending on which direction you're going. The key to the usefulness of the CMC equation is that the acceptability ellipsoids vary in size and shape depending on the area of color space in which the standard lies. The equation allows for visual non-uniform CLAB color space to be differentially subdivided into visually uniform ellipsoids for every point in color space. So now we can account for that non-linearity. Even though different parts of color space in the CLAB system are different, we can account for that using our CLAB equation. So again, this is the color tolerances actually defined by the CLAB equation. And you can see if you're a color matcher, you know tans and beiges are very difficult. You have to get very close numerically before they'll look right. And if you look in that part of the color space, you would see that they have very small acceptable tolerance volume shapes there. If it's blue-green, you can have a much bigger difference in the actual numbers and still have a match. The CMC equation allows you to take all those differences into account, where our LAB system wouldn't. Some advantages. The CMC color difference values were developed to agree with the visual perception of color difference for all colors. Use of CMC allows samples to be judged against the standard or control with the same one number tolerance for all colors. So now we're getting back away from, we had kind of gotten up to 12 numbers for our tolerance. Now we're getting back to one number for our tolerance. CMC total color difference and component color difference values are indicative of visual color differences rather than the visually non-uniform CLAB color space. So it correlates better with the visual observations. CMC allows the user to choose the relative importance of lightness difference in the color difference equation. So we can tweak it to correlate better with our actual data and our actual samples. Do that by adjusting the L to C ratio. That must be determined for each particular application, and it's based on the relative importance of lightness versus chroma. So in your particular application, there's a look at all the data and correlate it and do all the fancy mathematical stuff. You can determine the relative importance of the lightness versus chroma. Some applications, lightness is more important. Other applications, chroma might be more important. You can use a 1-to-1 lightness to chroma ratio, which is generally or recommended for judgment of color difference perceptibility. And 2-to-1 is used for judgment of color difference acceptability. In most cases where I've seen CMC used in industry, they use 2-to-1. And that's kind of the default value unless you find out a different value works better for your data than 2-to-1 does. But that's kind of where everybody starts at. So what happens when you change the L to C ratio, if you have a relatively low L to C ratio, we see the shape looks more like a cigar with the shorter axis being the lightness value. If we increase the L to C ratio, it increases that L axis so it becomes more rounded shape. So you're basically adjusting this lightness value here depending on how critical that is in your particular application. When you change the L to C ratio, you change the shape of the tolerance volume. So you need to specify that when you're doing CMC. Remember, when we were doing LAB numbers, we needed to specify what 4 things. You remember? The illuminant, the observer, 2 degrees or 10 degrees, the instrument geometry, or either Hunter Lab or C-Lab. In this one, you need to specify the L to C ratio, and you'll see there's one other thing. The CMC allows the user to choose acceptability tolerances for individual materials and applications. We don't have to use the same tolerance for every product. That's called the commercial factor. factor. That's the second thing that we need to determine to use our CMC. Commercial factor is the tolerance chosen by the user for the acceptable total color difference in a particular application. Different materials may have different commercial factors, but all colors of a given material would use the same commercial factor. So basically, how big does our tolerance volume need to be for this particular product? And once you set it, we can go back to using one number to say whether it passes or fails. If we have a higher commercial factor, we have a bigger volume. A lower commercial factor means a lower volume. But in this case, both volumes are the same shape. When we change the L to C ratio, we change the shape. When we change the commercial factor, we change the size. If we're kind of going back to what we said earlier, if we were a auto manufacturer which has tight tolerances, which one would we use? A lower commercial factor or a higher commercial factor as compared to our snow shovel, which is don't need the good tolerances? Which one would be for the auto industry? Lower or higher commercial factor? Lower one, right, because it's smaller. It has to be closer to the sample to be acceptable. The use of CMC is growing throughout the world for judgment of color differences in a variety of industries. Say the automotive industry is probably the industry that uses this the most. There's actually been some work done to adjust the CMC to make it even a little bit better. I don't have those equations yet. They're pretty much brand new. CMC is gaining widespread recognition as the best available color difference equation in existence today. Just as an example here to finish up, we could have 8 pairs of color samples that are made up, and each pair has a delta E of 2.0. So we're just going back to a regular delta E of 2.0. For all samples, the chroma and the lightness is the same. They don't have any difference in the lightness and chroma. All the difference is in the hue. Pairs of samples are spread out over the entire C-Lab color space. Well, this is kind of what it looks like. We have one set that is in this part of color space, number 1. Second set is here in the orange. The third set is in the yellow. And then we go through the green, through the blue, and 8 is moving toward red, and it's a bluish red or reddish blue. We have the same difference between them in delta E, regular delta E. So our delta E is the same for each pair. What we find is in different parts of color space, our CMC delta E, which is specified 2.1 L over C ratio, are different. Remember we said that pair number 2 is in an area where our eyes are real sensitive to differences in the numbers. So what that means is it has a very high value for delta ECMC, so it's saying that it's farther off. If, for instance, we said that, well, let's pick a number, our commercial factor for this product was 1.5. Okay? If we looked at our first set of numbers that are reds, right along the red axis, would we say that pair number 1 match? Yeah, because it's lower than 1.5. Well, if we move over to the oranges or tans, we would have the same delta E number, but what will we see? Our delta CMC is much higher, so we would say those two don't match anymore. And if we looked at them visually, we would probably see that the reds matched and these oranges didn't. If we move to the yellow, we would be a little bit higher, so that would what, not match. 4 would be yellowish green. Those would match. Greens would match. Bluish greens would match. Then when we go straight to the blue, now it doesn't match again. And finally the purple, blue and red, is right on the edge then. Even though the delta E didn't change, the delta CMC did to better correlate how we would see that visually. So it does a better job. Delta E is different paired depending on what part of color space they are in. The parts of color space where visual observation are more sensitive compared to the numbers, the DE CMC are larger. in the parts of color space where visual observations are less sensitive compared to the numbers, the delta E CMC are smaller. So it could be smaller or larger than our regular delta E, depending on where we are in color space. It helps you make better decisions. CMC is gaining widespread recognition as the best available color difference equation in existence today. Still not perfect agreement with visual perception, but better than CLAB. Values that must be specified when reporting CMC values to have meaning, like I mentioned, is the L to C ratio and the commercial factor. So those are only for our CMC.